Hi, I'm Nick Deveer. I'm with Group 1, and today I will be introducing the refrigerant charging experiment that we will be doing next class period. Being as if we live in Louisiana, we all have quite an appreciation for an AC system, especially the ones in our cars, because whenever those go out, it makes for quite an uncomfortable commute to school. Now, they go out for several different reasons, but the leading cause being a leak in an AC joint or an AC line. Whenever these develop leaks, the refrigerant will leak out into the atmosphere and reduce the overall efficiency of the system. Now, the picture on the right is an image of a very popular can of AC recharging, but more commonly referred to as death in a can by the Automotive Society. The reason why is they contain both refrigerant and stop leak. Now, your AC pump isn't exactly designed to handle this stop leak, so it can easily damage the pump or end up clogging lines further down the road. But the biggest killer is the extra amount of refrigerant, because the refrigerant entering the system is unregulated. If you have too much refrigerant in the system, it could either overwork your pump and reduce your efficiency, or it may, in extreme cases, make it to where the refrigerant is not reaching full saturated vapors. So how is it that automotive engineers determine the right amount of refrigerant in the AC systems? That's what we're going to be tackling next class period, by using an apparatus that resembles a very common AC system, with a few modifications, of course. Up here you see we have a reservoir with two valves on either side. The reservoir is going to contain some extra refrigerant. In our case, it's going to be R22 or Freon 22. The valve on the back side is going to allow more refrigerant into the lines, and the valve on the back side is going to take it away. Now, in addition to the reservoir, we also have 4 strategically placed sensors, both before and after the evaporator. These sensors are going to report the pressures and temperatures at those particular stages. We can then use this data to back out the coefficient of performance, or COP. The COP is easily calculated using the change in heat over the amount of work put into the system. Of course, the amount of work put into the system is easily defined as the change in pressure and specific volume across 2 different points. Now, you can get the specific volume by looking at both steam tables or at charts. They are going to correlate to both the temperature and the pressure at those points. You can also look into using the change in temperature using these sensors to back out the amount of heat change. Now, you can go further into this by looking at both pH and TS diagrams. By looking at the pressure diagram, you can look at the saturation curve, as we will be working within saturated liquid and saturated vapor points or states of the working fluid. You can then back out both entropy and enthalpy using these charts. It's a very straightforward process that we all learned, may not have mastered, but we all learned it in thermo. I went ahead and did a few back-of-the-envelope calculations to figure out some expected COPs. But in order to do that, I had to use a couple of assumed values. Now, last couple years that the experiment has been ran, they found that a common low pressure is 500 kilopascals and a common high pressure is 1200 kilopascals. I went ahead and took these as the assumed high and low pressures, since that was the only pressures I had to work with. I also assumed a CV of 0.57 kilojoules per kilogram Kelvin based on a few agreeing charts found online. Whenever I did the calculation, I also found it in terms of mass, so that I could easily plug in our low amount of mass and high amount of mass in order to figure out where in the ballpark our COPs are going to be. Whenever I did this, I also found that we had about 30 degrees Celsius difference across the board. My low COP was 4.67 and my high COP was 5.27. And in my opinion, these are rather high, because in a typical AC system, you will find that the COP is generally between 2 and 2.5. And this actually brings up a very good point, which is the amount of error that we will find. Now, seeing as if these were just assumed values, there's a very good chance that my math is off or I'm just not very good at thermo. But another good area of, or I guess not good, another area of uncertainty or error is in the sensors themselves, since there are going to be multiple sensors used. But all in all, between the amount of work put into this and the amount of issues that could arise, I believe that this AC experiment could be pretty cool. Any questions?
So, can you go to the apparatus diagram and point out where TL and TH would be?
Okay, so right after the compressor, there's going to be a high pressure in this area right here. And then as it comes through here, we're going to reach the lower pressure as it comes to the evaporator because it's going to be changing states. And I want to say that on this side, you're going to have the change in heat as it's absorbing the heat, and then it's going to evaporate it through. And
so at 2 you have the highest temperature, and at 3 you have the least?
I believe it's actually 1 and 3, if I remember correctly. I sat there staring at it for a while, and I will be honest, I failed thermo once. So I'm not the best for this particular experiment.
Where did you find that an appropriate COP was between 2 and 2.5?
Several different websites seem to agree on that, and I believe that it might have also been in the manual. I can't remember. I read through a lot of documentation, and they seem to agree that it should be trending towards 2.5. 2.0 is on the low side.
What does COP physically mean?
It is not really an efficiency, but the coefficient of performance basically just is like how well the system is working in accordance to how much work you're putting in. So the higher the COP, the less amount of work you have to put in to change the heat across the system.
Why do you think this COP is lower or higher than 2 or 2.5?
I just believe that a COP that astronomically high, you're getting 5 times the amount of heat out of it than you are putting work in it. And just from an engineering standpoint, and I've had some hands-on experience, it just seems like that's a lot of gain for a little bit of work put in.